Hello everyone, my name is Mattia Atzori Corona and I am a PhD student in physics in the University of Cagliari. I am very happy to be here today to discuss with you some constraints on electroweak physics that we obtained exploiting low-energy neutrino scattering data. So we are working on the framework of the standard model of particle physics. The standard model is an astonishing successful theory based on a few principles. However, the standard model is not able to provide an explanation for some observables like dark matter or dark energy, because that we can see their signatures, but we cannot describe them from a fundamental point of view. And even if we consider the particle physics perspective, there are a lot of open questions that are related to some particles that we know that exist, like neutrinos. For instance, we don't know if neutrino can carry an electric charge or a magnetic moment. We don't know what, and this is also very important in the context of the evolution of the universe, because new neutrino interaction can modify the expansion history of the universe at early times. And on the other hand, we don't know what is the neutrino mass, which affected the late time evolution of the universe, if a neutrino contributed to the matter content of the universe. But it is also very difficult to deal with the neutrino mass from the point of view of, so from the theory side. We don't know if there is a fourth species of neutrinos, so-called sterile neutrinos. We don't know if neutrino can be the key to understanding dark matter through the so-called dark portals. However, we don't know, there is something that we know about neutrinos, and it is that they are very elusive particles. Neutrinos do not like interacting with ordinary matter. However, there are some low-energy neutrino interaction that can help to unveil some of their secrets. In particular, in this presentation, I will focus on neutrino electric charge and neutrino magnetic moment, which are neutrino electromagnetic properties that can be studied by such low-energy neutrino interactions. First low-energy neutrino interaction that I want to consider is the elastic scattering of neutrino with electrons. This is a process which is very well described within the standard electroweak theory. And so we know how to write the cross-section for this interaction in terms of the axial and vector couplings. And you can see that there is a difference if we consider electronic flavor neutrino, because in this case, the interaction can be mediated by both the charge current or weak neutral current, so W and Z boson. But we can also have that in the case where we are considering the interaction of muonic and tauonic neutrinos with electrons, the interaction can only be mediated by the exchange of a Z boson. On the other hand, so the aforementioned formalism is correct if we are considering free electrons, but given the fact that we are dealing with bound electrons in the atom, we need to account for the atomic structure. This is usually done by means of this Z effective term, which accounts for the number of neutrinos that can be ionized by a given energy deposit Te. And this is also known as this term is also known as edge energies, because you can see the effect of this edge that accounts basically for the atomic structure, which is of the given atom. And this gives this shape for the cross-section of neutrino with a given atomic structure for different elements. Another very important process that I want to discuss is the coherent elastic neutrino nucleus scattering, also known as the sevens, which is a process predicted by Friedman in 1974. And this is a process very important where at low energy, where the wavelength of the Z0 boson that mediates the interaction is bigger than the size of the nucleus. In this case, all the nucleons inside the nucleus respond coherently to the interaction. And also in this case, we know how to write the cross-section for this process in a very accurate way. Here I'm reporting the value of the coupling of the neutrino with both protons and neutrons and accounting for radioactive correction. And you can see that the neutrino coupling with the neutron is much bigger than the coupling of the neutrino with the proton. So this means that the cross-section is roughly proportional to the number of neutrons squared inside the nucleus. And here in this plot, I'm showing a comparison between the 7th cross-section and for a very heavy element like tungsten, germanium, or silicon, and electron. And in this case, I mean, the 7th cross-section for a heavy element is about 10 to the power of 4 times bigger than the cross-section with electron as a function of the neutrino energy. So this means that this is a very useful process because the probability rate of interaction is much higher. So now you can wonder what are the neutrino sources that we are considering and the data in order to obtain the limits that I will present. The first neutrino source that I want to discuss is the sun, because there is constantly a very huge number of neutrinos that are produced by nuclear reactions inside the sun. So neutrino oscillae propagate and from the sun to the earth, and we have a mixture of electronic, muonic, and tauonic neutrinos. And those neutrinos are a problem for direct matter searches experiment because they represent a background. We are using the data from the Lux-Zeppelin LZ dark matter search experiment. This is a double-phase xenon DPC with a very huge mass of about 5.5 tons. This is a very low background experiment with a very huge background rejection power, a very low energy threshold of about 5.5 keV nuclear recoil, and this makes this experiment very suitable for studying new scenarios as it is sensitive to neutrino electron scattering data and to the process. Another experiment that I want to discuss, because I will present the constraints based on the result, is the coherent experiment. That is the first collaboration that observed sevens in 2017. So they produced neutrinos exploiting a sharply passed neutrino beam produced at the spallation neutron source, SNS. In this case, we have electronic and muonic neutrinos and muonic antineutrinos. And we will use the data that came from the cesium iodine detector. So those data have been publicly released in 2021. It is a 14.6 kilogram scintillation crystal located about 20 meters from the spallation neutron source target. And they provided also 12 sigma evidence of sevens. And so they are sensitive also to neutrino electron scattering, and they have a very low background and low threshold, about 7 keV nuclear recoil. Moreover, we will also use the data from liquid argon. So this is about 20 kilogram liquid argon detector located about 20 meters from the SNS target. It is a single-phase detector with a threshold of about 20 keV nuclear recoil, and the significance for their observation is about 3.5 sigma, while the previous one was about 12 sigma, so detection of sevens. However, due to the structure of the data, the liquid argon detector is not sensitive. In particular, the data that we are using are not sensitive to neutrino electron scattering process. And we will also use the data from reactor antineutrinos, because neutrinos can be produced through beta decay at reactor power plant. And in this case, we will use the data from the Dresden 2 collaboration that reported 2022 a signature of sevens, so using the data from a very low noise germanium detector with a very low threshold. So with all those data, we are able to study neutrino electromagnetic properties. So we know that neutrinos are neutral particles, so they cannot couple with the photon at 3 level. However, it is possible to write a vertex where the interaction is effectively mediated by a photon. So you can wonder if we have such kind of diagrams in the standard model of particle physics. This is not possible at the tree level, but if you consider a one loop diagrams, I'm quite sure that you will be able to understand which are the diagrams that in which interaction can be mediated by a photon, a neutrino interaction can be mediated by a photon. So here I will give you the answer, and you can see that if you insert a one loop diagram with two leptons and one W boson, or two W bosons and one lepton, it is possible to have an interaction which is effectively mediated by a photon. Those diagrams give rise to the so-called neutrino charge radius, that it is not the topic of this talk, because now I want to discuss some beyond the standard model theories that can predict neutrino magnetic moment and neutrino electric charge, which are even more exotic neutrino electromagnetic properties. So starting by neutrino magnetic moment, this is predicted to be null for massless neutrinos, but if we have Dirac neutrinos, so with the neutrino magnetic neutrinos are expected to acquire a magnetic moment proportional to their mass, according to this formula, even though this is a very small magnetic moment, to the order of 10 to the power of minus 20 per magneton. However, many beyond standard model theories predict a larger magnetic moment, and we know how to deal with it with the sevens and the cross-section and the neutrino electron scattering cross-section, because we have, from the theory side, we have to add this contribution to the standard cross-section, and the contribution for of the magnetic moment is proportional to 1 over the energy deposited in the detector. So this means that at low energy, this contribution explodes. So an experiment with a very low threshold is very suitable for testing these scenarios. So regarding the electric charge, we know that in some beyond the standard model theories, neutrinos could acquire a very small electric charge, but the stronger constraint comes from the neutrality of matter. So in this case, we know how to parameterize this contribution inside the seventh cross-section, and also inside the neutrino electron scattering cross-section. So there is a term, now we have to add a term which is proportional to the strength of the neutrino electric charge. On the other hand, if we consider the scattering of a millicharge neutrino particle with the atom, so if we are in the regime of the neutrino electron scattering interaction, the question that I want to address is to which extent can we rely on the free electron approximation corrected with the edge energies, because so the electrons are charged particles, and if we have another charged particles that is interacting, this scheme cannot be applied anymore, as I want to show you now. So there is a more sophisticated approach, which is so-called relativistic random phase approximation, which is an ab initio approach, which is able to improve the description of the atomic many-body effects. And you can see in this plot from this reference that the free electron approximation with the edge energies is different from this ab initio approach. On the other hand, there is another scheme, which is the equivalent photoabsorption approximation that relates the ionization cross-section to the photoabsorption one. In this case, we know how to parameterize this cross-section with this formula. And it is very similar to the ab initio approach. So in our results, I will adopt this EPA scheme. Now I will present you the results finally. So here I'm reporting the constraints on the neutrino magnetic moment. On the left part of the slide, I'm reporting the constraints obtained with coherent with seventh experiment. You can see that Dresden 2 results are much more stronger than the one obtained with cesium, iodine, and argon detectors. However, the constraints on the on the magnetic moment for the neutrino of both flavors are not the best limit compared to other experiments. On the other hand, the situation is different when we consider the limit coming from the LZ experiment, because LZ is a very low background experiment with a very small threshold, and considering solar neutrinos, we are able to constrain the effective neutrino magnetic moment, which is a mixture of the three flavor of the three flavor eigenstate. And in this case, however, the constraints are much stronger than the one obtained with seventh experiment on the left part of the slide. Now I will discuss the constraints of the neutrino electric charge. In this case, on the left part of the slide, I'm presenting the results obtained with seventh experiment, which are very competitive compared to the best limit. But on the other hand, when we move to consider the new results coming from mathematical experiments, the limits improve a lot, as you can see here. So now I'm presenting the state of the art of the constraints, also with some summary plots. You can see that there also recently there has been published a new result from the Xenon and Don collaboration that reported actually the best limit on the neutrino magnetic moment of the order of 10 to the power of minus 12 Bohr magneton, so 6.4 times this quantity. This is a very strong result, which is stronger than LZ. However, the limits from dark matter experiment are stronger than the one that exploit the seventh detector. On the other hand, for neutrino millicharge, the Xenon and Tom collaboration didn't report the result on the neutrino millicharge. So the results that we reported on this quantity are with LZ are the world leading constraint for the moment. So to conclude, seventh experiment allow one to set very strong constraints on neutrino electromagnetic properties, and also the complementarity with the dark matter experiments is very crucial when one considers neutrino electron scattering as a signal. And it is we understand that a low background experiment is needed, also as well as a very small and very low experimental threshold. And with LZ data, we have been able to obtain a very strong constraint on both the neutrino magnetic moment and neutrino effective neutrino millicharge. So thank you for your attention.